Hello, here we are, Unit 7, the valve assembly. This here is a pressure relief valve. It's a machine part that we're going to do. So we're on unit number 7. Let's take a look at our part and assembly. Here we have a valve assembly, and in this valve assembly you can see it's a pressure relief valve. Say, for example, I might have something that is high pressure and I want it to release the pressure. I might have a hole, and well, let me just draw something for you so you can see how it works. I have a hole that I would put this thing into. Goes in here like this, and I'm going to press the thing into the hole, and when I press it into the hole like this, this is inside of a hole, and this pressure relief valve then is inside this hole. Fluid could come in this front way, and when it got to a high pressure, what it'd do is it'd push against this little valve, and you see I have some springs back here. We'd come in, go through, and then be able to come out through the back, right? So it's just a pressure relief valve, something like you would see in your water heater. And what we have is it's composed of a couple of pieces. What we have is we have the body here. That would be one. Then we have the plunger. This here is another one, right? That one there. And then we have the end cap. So it's a fairly simple simple part that we have. We're going to talk about those three parts. You know, there's number 1, there's number 2, and there's number 3. Now, an important thing here, if you notice here, this end cap must not overhang the housing, because what we're going to do is press this inside of a hole. And when it's pressed inside of a hole, you see, we didn't want this to overhang, because if it overhung, then it would hang up and maybe gouge the edge of the surface, or maybe cause this part to move over. So they wanted, that was a criteria, that cap always has to be below, right? That's important. And there is some tolerances you have to worry about, right? That gap is going to affect what that is, and the size of that, and the size of this, and the size of this. But when we get into that problem, we're going to look at it a little bit later, but that's something you should take. We also have the spring. Spring's going to have geometric tolerancing applied to them also, you know, for size. And but we're not going to do the spring on ours. All right, let's continue on here. We'll take a look at our next picture. This here is a little graphic of how the thing works. I have a little animation, so let me show you this one, and just sit tight, and I'll show you how this part assembles. It'll give you a better idea, because it's important that if you're the engineer, you understand how the part works in order to be able to tolerance it. We're looking for function. You remember from our past, you're looking for mating surfaces. You're looking for the most functional mating surfaces to be able to select as your datum. So you want to be thinking of datums as we're going to go through this part. All right, let me start up the animation here, and you can see there's our parts. See, the end cap goes over the plunger. Plunger goes in, fits up. There's our plunger inside. There's some fluid coming in. It opens up, closes again. Opens up and closes. See that front there? That's a seal surface. Okay, here's our another little assembly here. That was just assembly to show you how it works. You notice, as I mentioned here earlier, that this end cap must not overhang the housing. What we're going to do is take this part and we're going to weld it here. When we take this and we put it in, it's an inseparable assembly. After we get all of the parts manufactured, in the assembly process, let me tell you a little bit about it. We take that end cap, we put it on, and then there's going to be a little gap here. We're going to weld, probably EB weld that all the way around, and we don't want it to overhang. We got that little groove there. And so in order to put them together, we're going to have well, probably in the assembly is some clamp or something, some fixture to be able to put them together, hold them tight, and then weld it, and then let them go. Because obviously if we push that in, this is a loose fit in here. If we let it go, boom, that'd pop out like a jack-in-the-box, wouldn't it? So we'd hold that in, and then we'd weld it all the way around. And you have this drawing in your workbook, in your student workbook, so you make sure you read over all of the details, and you look it over very clear what the functional requirements are. So you can't tell me later on that you weren't sure, you missed something. The idea here is you're the engineer, you read over all the functional requirements, and that's the way you're going to tolerance it. Now this is going to be a seal surface we have up here. You can see where that plunger hits this face over here, or this diameter. And so that's going to be an important seal surface that we're interested in there too. Some of the other fits and things that you're going to have, you will be able to figure out what your tolerances are going to be. And perpendicularities, and give a good shot at it, what you think, do your best guess, and then we'll come up and we'll talk about it. All right, so what we'll do is let me show you how this part works here. This here is just a 2D animation. You see here the fluid come in, it pushes the valve back, it pushes back a little more, then it closes up again, right? All right, what we're going to do is we're going to start with this piece first. This one here requires some geometric tolerancing on it. Now, we're going to do it piece by piece. I'm going to let you go in and pick your datums. In fact, I'm going to let you tolerance this one up the best you can. Just take this piece alone and tolerance it. Then I'm going to come up and tell you what I did on mine. You can see how the whole assembly works. Make your best guess on what you would pick as datums. Then I'll show you what I picked. Maybe before we get started too, I have a little model of this part that I'd like to show you, so you can again get a good picture of it. Here's the three pieces that I have. This is the valve housing, the one you're going to do first. Here's the plunger that I have, and how it works again is the plunger goes inside of the valve housing, it fits in, and then I have the end cap that goes on. First of all, you'd have the spring, right? The spring would go on here, and then I would take the end cap, put it on, and then once it was on, we're going to have some type of a clamp and assembly where it's held up tight, and then it's going to be welded all the way around. Then this thing fits inside of a housing, right? That's how it works in the end. Fits inside, and then the plunger works inside here. As you can imagine, it goes back and forth. All right, so you have a pretty good idea how this thing works. You might have with you the model. Depends if you have the models or not. But if you do, you might want to take a look at them yourself, pass them around. And the ideal thing would be is if you're in work groups. If you're in work groups, to get down and take that assembly, lay out the parts, and then see how you're going to tolerance this first part. So I'm going to give you a few minutes. You take your best guess on this one, and then we'll come back and we'll talk about it. So see you in a minute. All right, we're back here. We're going to take a look at the valve housing and see what you did. I'll show you what I did and my thoughts on it. First of all, remember we always start this off, we have to select the datum reference frame. So this is what I did is I picked the inside diameter is datum A. Now why I picked the inside diameter as datum A, I see that in our assembly for sure it mounts up against that face. That's for sure. This assembly does. And that is an important face. And if you pick that, well, that's a decision that you made, and it doesn't mean that it's wrong. It's just another way to be able to look at it. Now, what I picked is I picked this diameter, that inside diameter, and why I did is, first of all, it's a long diameter rather than that face. And sometimes I think about this is that it is important that that face comes up against, but you notice if I would have called that the datum, that face the datum, then I would have had to come into that bore, because I'm relate to features, I would have had to say the bore is off perpendicular within so much. Now, if I would have said it was off perpendicular within so much, right, because that'd be the way we'd relate to datums, then the way I'm designing this thing, I'm almost imagining that this face is correct, and then the axis is going on off on a direction like this. And but somehow it's hard for me to comprehend how I'm going to put everything together. You see, I think of the guts inside of it, and the guts inside of it, I have a little shuttle. I have this diameter, and the way the shuttle moves, it pilots on this diameter, and then it really pilots on this diameter, our plunger, and that fits on here. So I saw the axis is the line that was the most important to me, the thing that I saw things moving back and forth. Because later on, when I'm going to come in and I'm going to tell you where I want this surface, now I have that as the face. Well, really the plunger slides in and out. Then I would have to switch it to the primary datum being this diameter, and then I would end up having two datum reference frames. And what I try to do as best I can is try to be as clever as possible and try and do it with one datum reference frame, right? If you can grab the part with one datum reference frame and do it all together, that gives you the best part. So this is what I did. I picked that one there as my datum A. Now, I picked that as a datum A, and ideally you would qualify that surface. Now, I could have put a cylindricity or I could have put a roundness on it, right? But I thought that the size tolerance on here from 1/266 to 1/265 was good enough. That controlled the roundness, that controlled the cylindricity within that tolerance, right? So that is enough to be able to, that gives us size, and it has to fall within the limits of size. And if you remember from our fundamentals class, I think that's in Unit 4 in the fundamentals workbook, I talk about it, and that's enough of a control on it. All right, let's see what I did next is I called this face here then datum B. And I saw that as datum B. I guess, you could call this diameter here where the plunger hits as a datum, but, again, it's a contoured surface. It's, well, not a contoured surface, but it's an angular surface. How do you find that spot over there? And I thought that the best here for me was it was easy to get a hold of, that back face. And, I mean, that's really where the mating part comes up against. So I called that one off as datum B. Now, if I called off as datum B, I have to qualify that surface. This was my primary datum. It gives me an axis through here. And now this face, how perpendicular is it? Because remember, if you don't say anything, you haven't said. Nobody will check it. So what I'd be interested in is that how much that can be off, because that's going to tell me when this end cap comes on, the end cap is going to cock a little bit, right? It's going to cock whatever that perpendicularity is, so I'm going to put something on that face, and I did that, and I put a perpendicularity on. And I said that was perpendicular within 1. Now, if it's perpendicular within 1, you see how long that face is and how the difference on the length of that pilot. So that means that, just kind of approximately, remember from our stacks class, you can kind of see what the effect is, how long that face is, what the distance over here. It's probably going to tilt inside of the hole by probably half that amount within 5/10. All right, this here is our A, this is our B. Now I have my datums. The origin of the datum reference frame would then be someplace right around here, wouldn't it? That would be I datum. Now I have my datums. I don't need anything for anti-rotation. This happens to be a round part. Now I'm going to start locating things relative to the reference frame. So first of all, I put all dimensions, all untolerance dimensions are basic. That's probably the way I would draw this thing, right? Everything is drawn up. All of these, if I drew it up in CAD, everything would be basic, or the nominal numbers. And the only places I have is size. This here is size because I have a certain size because the little shuttle is going to go inside. And this here was size. I had to have size here, right? Because that's going to be the press fit into the hole that I'm pressing it into. So I got to have size here, and I have to have size here. Everything else is basic, and that's where I'm going to put the geometric controls on. All right, so the next thing I did was put a profile, and I'm going after the most important things first. So you see this area. This is the area in here that where I have the seal surface. And so on that surface right there, this is what I thought is I put what we call a composite profile. In composite profile, we talked about that in the fundamentals class. In the fundamentals class, I think that's in Unit 12. So you might want to have your fundamentals workbook if you're not sure what this means. But basically what I'm doing is I put a profile, and I said profile within 5 thousandths in relationship to A and B. So all that is a tolerance zone, and the tolerance zone would be 5, 2.5 on either side of that line, right? And it's within 5 to A and B. And then the next level here, what it says is now it's profiled within 1 in relationship to A. If it's within 1 in relationship to A, that's just to itself. So really what I'm doing is I'm locating that surface within 5. So what the engineer is saying is that surface can move in and out within 5, but then the surface itself relative to around the axis, it has to be within 1. And then I put this occurs between A and B because somebody said, well, where does it go and how far does it go? So I just put it in an area here. See, and there's my point A, and there's my point B. Then I give you some basic dimensions. So it's just in this area here, right? So how far it goes. So because that's the only place that it contacts, we don't need everything else. Now manufacturing, when they cut the part, they may cut more, but we're saying the inspection portion of it, we're just checking this area over here. So this is what we call composite profile. And what it did, the upper one located the surface, and the lower one then you refine the surface relative to just A. Now you could probably have another one on here again, maybe within 5/10 just to itself, if you thought that was necessary. Right? It could be as many as 3 tiers on there. Next thing I did was I took this diameter. This here was, now what was that diameter? Remember how we're tolerancing this part. We're starting from the inside out, the thing that's running on the inside. And the outside then, this was the diameter that we're pressing inside of the hole. Remember where it actually mounts. And this here I just located within 1,000. Now I located within 1,000. I didn't put an MMC. MMC to me doesn't make sense here, right? Why would you have maximum material? What you're saying is smaller it gets, the more it could be off center. Now I have to worry about wall thickness over here. So that would be regardless of size. And then the datum, of course, you know, as the datum gets bigger, as this hole gets bigger, you can get datum shift. Well, I don't want any datum shift. That doesn't even make any sense here. I mean, for what function would that give me that it's larger? So you notice in a lot of cases here, I'm not using MMC on the datums. It depends how it works. So I didn't have MMC here on this datum, and I didn't put MMC here. It's just not a functional requirement here for me. And I put position because I had to have this size. This size was important to me, right? This is a press fit size that they're going to tell me you have to have that or it's not going to press into the mating part. And this tells me how much it could be off. So this wouldn't be appropriate to be a profile tolerance. This here has to be a size tolerance. All right, let's see what else we do here. I think next thing, I located where that front face is. Remember our datum was down here. And this here was, what is that really saying? It's plus or minus 5, right? See that 265? Well, I'm not putting tolerance on a dimension. That's not how it works. What you're saying is where the surface is. The engineer is saying that surface is supposed to be 2.625, and then saying that surface has to fall within that band, and that band of tolerance is 10 thousandths. So it's really just giving it a length. And maybe to just show you that, the tolerance zone then, it's just saying this is your datum. Datum A was this line that they come across here, right in the center. Let me make that a little bigger so you can see it. That was my datum axis, right? That went right through the center here. And then datum B was this face over here. That's my datum B. My origin was right here. And then in the front here, that profile just saying that surface can be out 5 or it can be in 5, right? That's your tolerance zone, and that's your tolerance zone of 10. So you notice the way this profile tolerance is working. You're not putting tolerance on its dimension. That's not the way geometrics works, right? The old plus or minus put tolerance on a dimension. We're putting tolerance on the feature. You're pointing to that feature right there. Are you saying, see that feature there? That feature has to fall inside of a tolerance zone that's 10. So just stay in the lines, right? Just stay in those lines. It's kind of like manufacturing. You know, when you make the part, there's your tolerance zone. Stay in the lines when you make the part, right? Stay in those lines. What I did is well, I'm pretty much done. There was nothing else to control here. Then I put a tolerance on here, and I said all untolerant surfaces are profiled within 10. So everything else that I didn't control, you know, for example, this diameter is within 10. As a matter of fact, when you look at it, this one here, probably I didn't need this one on, did I? If this one here covers everything else, all untolerance dimensions are 10. But it could have been where this one could have had a larger number on it. So this here may be a little better to see. You see our tolerance zone, and our tolerance zone, remember for this one, looked like this. So your tolerance zone, you had a tolerance zone of 10. So that zone of tolerance would have been 10 thousandths there. Remember? That would have been your zone for this one. Now this one, when you say profile within 10, like I said earlier, we probably wouldn't need both of these, and maybe that should have been 20 because we already have that one called off. I mean, it doesn't hurt anything, right? But this one here is kind of the catch-all. But when you say profile within 10, remember what that does is on this diameter then, since that doesn't have any tolerance, that would have given you a tolerance zone over here within 10 also, wouldn't it? It would have been 10 on that side, and it would have been 10 on that side, wouldn't it? So this overall then, well, how big could that diameter be? Well, it would be 0.625, and then it would have been plus 10 or minus 10, right? So that's really plus or minus 10. The reason is remember that 625, and this surface can go bigger by 5, right? And bigger by 5 on this side, so that'd be plus 10 or it could be minus 10. So when you say profile within 10, you know, you say all intolerant surfaces, just remember that something like this surface, it can only move out 10, but if you have on a diameter, that one could have moved more. Sometimes on some of the drawings, you'll see a little bit later, you know, if I'm concerned about that, I'll say diametral surfaces, it has to be within 10, but then all other surfaces have to be within 5, you know, then or some other number, so you can distinguish between diametral surfaces and surfaces like this. All right, that finished the housing. Tell you what, where we're on next is we're on the plunger. And I'm going to give you a few minutes to do this plunger. And I want you to take a look at it. You see where it fits inside of there. What I'd like you to do is you select your datums the way you think that that part would work. And I want you to think real functional here now. You notice how it fits inside of the assembly, what you think. And the idea is to let you go ahead and do it, and then give you some examples of how I might do it. Just give you some thoughts to think about. You know, that another approach, and you can take a look at it and see if you like what I did. So I'm going to give you a few minutes. I'm going to let you do this one. Put your tolerances on, and you might use some of the techniques that you just learned in what I did on the housing. And then we're going to come back and see what you did. All right, we're back on the plunger, and let's see what you did here. This is what I did. What I did is if I looked at it inside the assembly, the way that part was fitting in the assembly, take a look at it. I'll give you an example here. We look at it pretty close. You see it sitting inside the assembly there? And you see the way the plunger is fitting in? What it does is it fits on two diameters at the same time. And probably if you looked at it real close, you noticed that too. It fit on the front diameter, and it also fits on the other one. It fits on both of them at the same time. And if it fits on both of them at the same time, I suppose you could have called the rear the datum, right? Or you could have called the front surface the datum. The only thing is, the front surface, you notice it's pretty short. In the rear surface, where it actually comes in contact, it doesn't make much contact, so that comes in pretty short also. So what I did is just a novel approach, just to give you some ideas, get your thoughts a little, thinking a little bit here. I did it like this. I called this diameter here as datum A, and I called this one here as datum B. And when I did that, I called off, and I'm going to set this thing up as an A-B. Right? So if you remember here in our fundamentals class, we were able to do that. And when I do a A-B kind of an arrangement for the primary datum, it said set them both up at the same time. In other words, for example, if you were setting this up, you know, in a V block, you'd set a V block here, and you would set a V block over here. You'd have to have, you know, shims between the V blocks. Or another way on a coordinate measure machine, what they would do is they would touch this diameter, they would find the center, touch this one and find the center, and it would be the axis through both of them. And they're of different sizes too, aren't they? So this here is just, I call this one B, and I call this one A. Now I cover this pretty extensively in the fundamentals class. That's in Unit 14. And there's an example that's very similar to this one in the fundamentals in Unit 14. If you need to look that over, you can do that there. Now I had to relate the two features to each other. So relating the two features to each other, you see I did it like this over here. I called that one A, and then I said it was positioned in relationship to A-B, and I did it at MMC. And then I also did the other one the same way. I hooked the other one relative to A-B. Now this is not to itself, right? This is, sometimes I have people in the class, they say, well, you're hooking it to itself, but you're not really doing that. And I cover this extensively here in Unit 14 in the fundamentals workbook. You can take a look at it. You probably should have a copy of that workbook so you can go over and read over the text. There's only so much review I can do here. But you notice what A-B is. B is on one side. This one here is B. This here is B right here. And this one here is A right here. And you notice that if you took two diameters will never be in line to each other, right? You could never, you could never make two diameters in line. I can make a dot and a dot in line, right? I just draw the line here, but that's not what we have. You have an axis here, you have a line, and you have a line. So you know what's going to happen if you have two lines. If you had two lines, you're going to try and get two lines to line up. But now we have to magnify this and look at it very closely. But what you're going to get is you're going to get a line like this, and you can get a line like this. And no matter how you try and do it, you're not going to get two lines to line up. So what this one says is that you have to set it up to the A-B axis. Now I'm going to just do it mathematically here so you understand it. And mathematically, in order, how would I find the center of two lines that look like that? Well, mathematically, what they're going to do is they're going to take the smallest cylinder they can get around those two, take the smallest cylinder around it, then they take the center of that, right? So you see what this is? This one here is B. We'll call that one off. That's our B. And you see what that one is? That one is A. And what is this? This here is A dash B, right? That's our A dash B line. So if that's our A dash B line, you see what I'm saying with this diameter? I'm saying that the B has to be positioned to the A dash B line within 0 at max material. So at its smallest size, it has to be on. As it got larger by 1, you see it could be off by that. There's your 1,000th tolerance zone that could be off. And the same thing with this one. This diameter right here has to be off within 0 at max material. So at its largest size, it has to be on, but as it gets smaller, then it could be off. And so this tolerance zone could be as big as 1,000, right, if it comes in at its largest size. Okay. So that's what we're saying. Now, that was a real quick review here. If you had that, take a look in the fundamentals, it'll talk about that a little bit more. All right, so that was my A-B. And then this face I called off as datum C. And again, I called off that face as datum C because, well, there really was nothing else. It did hit over here, but getting on a spherical surface and calling that a datum, that's pretty complicated, and the repeatability that I would get. Not that, you know, I'm trying to make inspection easy. That, I mean, you know, they will do whatever you ask them to do, but, you know, it just, am I going to get reliable answers from them? So I saw that it was, you know, this was a much more reliable surface, and, you know, functionally wise, the spring hits here, so I call that surface off as datum C. Now, of course, I would have to qualify that feature, and you know what's going to be there, right? There's got to be a perpendicularity, doesn't it? So I put a perpendicularity on there within 2. So that means while I'm on the A-B axis, that face, I have a tolerance zone, it can be off within 2. And then the datum you contact on the high points. So there's my datum reference frame. It's been established. And once it's been established, then all untolerance dimensions are basic. And then I'm going to go around and start pointing to the things that are important. And I did the same thing, right, on the inside over here. You see that plunger? This time what I said is it has to be located, that surface, between A and B. And I didn't need the entire surface, right? It was just in an area here where it matched the meeting part. So I just said in that area there, it has to be within 5 to A-BC. So on that datum reference frame, while you're holding it, I want you to hold it on those 2 diameters, and then make sure that that surface is there within 5. And then to itself, and relative to the axis, it has to be within 1. And I said between A and B. You see there's B and there's A, and then I defined here, you know, 30 degrees away and where that surface was. So those are the basic dimensions. All right, then let's see. Then everything else, I just put a profile on here, and I said the profile on there was within 10. Everything else that wasn't controlled, you know, the little flutes in here and some of the other surfaces here, that the important things I called off, and then the other ones are just a block tolerance. I give you a lot more tolerance there. All right, that finishes our plunger. So you know what's next, the end cap. I'm going to give you a few minutes to do the end cap, and then we're going to see what you did. So and once you put the tolerance on the end cap, be aware here that what we're watching for in the end here is this end gap here. Remember, that can't overhang. We always wanted one to be behind the other. So I'm going to give you a few minutes on this end cap to go ahead and do that one. Put your tolerances on as best you can, and then come back and I'll show you what I did. All right, we're back here on the end cap, the student exercise, and this was our part. Fits inside here like this. It's that blue one on the end, and we're going to see, I'll show you what I did. Now, I saw that this part mounted up against that face in the detail. Now, you know, it did fit in this hole, that's for sure. You know, there was a pilot. But if you really take a look at that pilot, there's clearance between that pilot. There's clearance between this and this one over here. And remember how I told you before that when we were going to put these together to do that welding over here, we were going to have to clamp those two together, right? We were going to have to clamp them down. And when you clamp them down, what's going to happen? Those faces are going to come together, right? We probably have a gap requirement there that the manufacturing is going to tell us that we have to in order to be able to weld this together. So when I saw this one coming together with that one, I wanted to clamp these down tight, and I'm expecting the faces to come down tight, because there's clearance between this diameter and this diameter on the part. So I called that one a datum. And you see it is the longer surface too, isn't it? Look how long it is, right? It's probably double, you know, 2.5 times longer than what that diameter is there across there. So I saw the face as being the primary datum. Secondary datum, of course, would have been this diameter right here, because that's where it locates. See how it fits inside? Where it's at, remember the mating surfaces, it actually mounts inside of that. That's where it locates. That was my datum B. Then, of course, I had to qualify the surfaces. So A, what are we going to put on datum A? It's got to have some kind of a qualification on it. That's where I'm starting off, so I would just have a flatness on it. And then B, what am I going to put on datum B? Well, there, I'm just going to put a perpendicularity on. And remember what I said that I like to do here whenever I'm working with pilots is that perpendicular within 0 at maximum material. And basically, remember what that's saying is what you're telling manufacturing is that when this thing comes in at its largest size at 1.264, I'm expecting it to be perpendicular to the face. Kind of like the good old days. Remember the good old days? You would just say this is A and this was B and never said this was perpendicular or anything. Well, what did you mean? What were you thinking? Well, you were thinking with your eyeball looking right at that face, right at this face, looking in this direction right here, perpendicular within 0. So that means that 264, it has to be perfectly perpendicular. As it gets a little smaller, then it can be off. So if it comes in at 263, then it can be off. That's probably, this here is going to be a turn part anyway, and you can imagine when they're going to turn the diameter in their face, probably not going to have too much of a perpendicularity problem. And they need all the size that they can get here, and we only have 1,000. That's all we're having. This is a small precision type part here. All right, next I had to come in and put all untolerance dimensions basic down at the bottom. And then I came into this diameter, and I said that that was going to be positioned. And why I put a position on here? Why I put a position on here is I needed this size. And I needed this size because this was the diameter a plunger fit in, and I needed a certain fit, right? You know, slip fit, running fit, press fit, you know, this is a size. I needed this size, and then this told me how much it was off. And again, there's no maximum material condition here, is there? I mean, if this hole gets larger, it can be off more. It's going to take my shuttle off some more. So no, it doesn't make any sense to put any maximum material condition here. And the same thing over here on the datum. That datum should be regardless of feature size, just the way I have it. If it gets larger or smaller, you can't have any advantage of more max material. So this is regardless of size. You notice I'm trying to keep things on the center. Everything is centered. That is not the place for max material. Max material is for clearance holes and for loose fitting assemblies. You know, similar to the brackets we had that we talked about before. But on this one here, I don't see it. All right, let's see what else we had. The outside surface here, they did is I put a profile of 5 thousandths on here. Now, why a profile? Why is this a profile and this one here a position? You know, why is the difference? Well, this one here, I didn't really need a size. You see this? You see that? All I'm interested, remember our design requirement is that it fit inside of the hole, it fit on my datum, and then I was looking where that outside edge is. Just don't let that outside edge get too big or don't let it get too small. That's it. I didn't need a size and then tell you how much it could be off. This one I needed it. Remember why? Because I have a fit. Something fits in it, and I needed to know what the fit was, and then this is the location of it. So this tells you what it is, this tells you where it's at. This one here, it just said, just don't let the thing get too big and don't let it get too small. So this one here would be more appropriate for a profile. Now I cover this, why I would use a position and why I would use a profile, the difference between runout and the difference between concentricity. All of that is covered in Unit 14 in the Fundamentals Workbook and coaxial tolerances. You might want to read that over again. That's going to talk about that a little bit more. Right? So this here is why I used a profile tolerance on there. Okay, and then I guess what else? I came in and told you where this front face was. You know, not too far. I guess it gives you the spring tension. That's about all. It profile within 5. And this here is my solution down at the bottom. I put, unless otherwise specified, everything else had a profile of 10. So that's my requirement. All right, what I'd like to do next, this one here is tolerance, to use my drawings. If you see my logic, what I did, and how I come up with the tolerances, maybe just to give you some ideas. So let's take a look here at our next problem. Our next problem here is that with the numbers that I used right now, we did not want that end cap to overhang that housing. Remember, that was a design requirement there. Now, with the numbers that we have, will that happen? Let me show you what could happen, right? If our housing was a little bit smaller, you see how it could move from one side to the other, and it's important that it never overhung. That would be an important thing. So what I would like to have you do is do the calculations here. And this here is our 2 parts, right? There's the end cap, there's the housing. You have these drawings, you have the solutions to these drawings, and you're going to use my solutions, and I want you to tell me, I want you to do a little stack up on this thing, right? Part of this. And ideally you should have had the stacks course so you understand how to go about doing these. You can do a little bit of a review, and I'll show you how to do them the best I can as a review, but for some of you who had the stack class, this should be quick work for you to be able to do. And what we want to do is find out, does that overhang there? So using the numbers and the geometric tolerance that we have, can you calculate that for me? I'm going to give you a couple minutes to go ahead and do that calculation, you know, which would be certainly a requirement that an engineer would do. Just quick calculations here and there to make sure that doesn't overhang. And I'll come back in a few minutes and you tell me what our end results are. So we'll see you in a few. All right, welcome back. We're on the valve assembly, and we were going to do a little stack, remember? And I gave you some time to be able to figure this out. And if you're familiar with the stacks program earlier, you might want to be able to get a copy at least of the workbook, and so you can follow along. I'll take it easy here, and I think you'll be able to see the logic we're going about and how we go about doing these stacks. This one here was a fairly easy stack. Now, do you notice if you analyze the assembly here a little bit, I mean, what else? You see that joint in there? I mean, these two could be perfect, but then we also got a joint that caused some misalignment in here. Let me actually draw that here a little bit. You see where the end cap fits inside of the housing? There's a little bit of a gap in there. Remember, there could be some clearance in there, and if it was, the outer boundaries of each of those two features could rattle a little bit. So what we have to do is watch that joint in there also. So let's take a look how I would go about doing that. What I would do is, if I was looking as to analyze the assembly, is that I've got what is my two initial features? What is it that I'm interested in? I'm interested in the outer boundary of this one, or let's say the inner boundary, the worst case inner boundary that I could ever have. And on this one, I'm looking at the worst case outer boundary that I could ever have. So, and then once I found out the inner boundary of that one, then what I've got to do is I got to figure in that joint. So let's do, what I'm going to do is I'm going to try and calculate what the inner boundary of this one is and the outer boundary of that one is. And that could be done just like this. Right now I could actually go up and do a stack tolerance form, but some of this stuff is so simple you can almost do it just on your fingers and your toes. So over here, for example, what I'm going to do is I have to find out this housing. See that housing? And I'm going to find the worst case inner boundary of that housing. So I come down here and I take a look at that housing, right? And they're mounted on the datum in there, right? So the two parts are mounted. See, that was the datum on this one, and this is the datum on this one, so that's where they're matching. If you notice, if you put the geometric tolerancing on correct, when you do your stacks later on, boy, this is simple stuff, right, to do your stacks. So let's take a look at this outer boundary. Or we're looking for the inner boundary on this housing, the worst case, the smallest it can get, to make sure the cap doesn't overhang. So the smallest this diameter could ever get would be 1.500. Remember, and you remember our tolerance stack form for regardless of feature size, and this is the regardless of feature size modifier. It just says that if you have 1/500, you just subtract the position tolerance. So the smallest diameter, which is 1/500 minus the 1000, that would be 499. That's the smallest inner boundary that you could ever have. And what that is that's this diameter, right? If it was off center, right, relative to your datum, it could be off center. And the inner boundary that it creates is no smaller than 1.499. This is on a diameter. Now we're going to take this cap, and we're going to take the worst case outer boundary on this cap. Well, the largest, well, this is a basic dimension, so 1.491. And then it has a profile tolerance on it within 5, so that means it could get larger by +5, right, because it's 2.5 on either side. So the largest that could get relative to the datum reference frame is 1.496. So if I subtracted those two, you'd find out that we have a clearance of 3. So that means that that cap right there will not overhang that housing. We have a clearance of 3. Now when I say 3, this is on a diameter, right? I'm always doing diameters. I didn't put my diameter symbol because I just do diameters all the time. It's just, what else is there? We do geometric tolerancing and total tolerances. So I got a clearance of 3. So we should be all right. The only thing is, we remember now, what else could contribute to that misalignment? What else could contribute? A contributor would be this joint in here. You see where those two are going together? So what we have to do now is we have to take that housing and we have to find the largest that that housing can get and the smallest that that cap could get. And that's going to give us a rattle inside. And that rattle inside will also contribute. So let's go in and now check that out. And what we got to do is do it like this. We're going to find out the worst case outer boundary of this housing now. That means the largest it could ever get. This is our datum, and the largest it could ever get would be 1.266. So there's the outer boundary of the housing. And now we're going to take a look at the end cap, and we're going to take the inner boundary of the end cap. And the inner boundary of the end cap in this case is just perpendicularity. The smallest that thing could ever get would be 1.263. So if it's 1.263, we find out that that joint is 3 thousandths. It's a joint, so that means that could cause that to misalign by 3. If it does, we already have a clearance of 3, so the 2 negate, and we find out that right now, the way it's telling us, we have a line-to-line condition here between those two. So it looks like this thing is all right. Our design was good. So everything should be pretty straightforward. All right, I guess that finishes. We should be proud of the job that we've done. We got another job done. And we have another one coming up. We have the mixer. I think you'll enjoy the mixer. It's a little bit more complex parts, a lot of parts going in there together. So that's going to be next. So we'll see you for that one.